Okay, welcome back everyone. In today's video we're going to be again looking at the MathCounts 2024 State Sprint Round. And here I'm going to be looking at the 10 hardest problems, problems 21 through 30. These are the ones that are very, very difficult in some cases. So let's jump right into it. And again, just a reminder to pause the video when you see the problem so you can try to work it out on your own. Alright, this one says, this is number 21, it says, what is the greatest prime factor of 9 to the 6th minus 1 that does not divide 9 to the 5th minus 9 cubed minus 9 squared plus 1? Okay, so this problem is going to test your factoring abilities, and the first trick is to factor this one. If you consider 9 to the 6th as 9 cubed squared, you can think of this as a squared minus b squared, where a is 9 cubed and b is 1. So you can factor a squared minus b squared, so let's just write it out. A squared minus b squared, I just didn't need the parentheses, is equal to a plus b times a minus b. Alright, so again, a is 9 cubed, b is 1. We have 9 cubed plus 1 times 9 cubed minus 1. And one thing you can do is try to see if either one of these is also a factor of this thing over here. So, yeah, I guess what you'll notice here is that the power of 9 here in these different terms, we've got 5 and 3 and 2 and 0. And these are separated by 2, and then these are separated by 3. So yeah, it's probably going to be 9 cubed plus or minus 1. Let's see, what is it? So let's say 9 cubed plus or minus 1 times 9 squared plus or minus 1. Let's see, what is it? So if I did 9 cubed times 9 squared, that would give me the 9 to the 5th. The minus 9 cubed means this has to be a minus, so let's fix that. And we'll just fill these in when we have them. So this is a minus, so that you get a minus 9 cubed, and then minus 9 squared, that means this one's also a minus, so that we get a minus, and then the minus 1 times a minus 1 is a plus 1. So this can be factored like that, and this one can be factored like that. Alright, so the thing they have in common is this 9 cubed minus 1. And what we're looking for is a prime factor of this one that does not divide this one. So we can kind of ignore this part here. Alright, we can ignore that part. And we're going to try to find a factor of this that does not divide this. So at this point we probably just want to figure out what 9 cubed plus 1 is. Let's see, 9 cubed is going to be, let's see, 729. I should have that memorized right off the top of my head. So 729 plus 1 is 730. And let's see, so 730, what are the prime factors of 730? Well, we've got 73, that's prime, times 10, which is 2 times 5. And then what do we got over here? We got 9 squared minus 1, we can figure out what that is as well. This is 81 minus 1, this thing is just 80. So we're looking for the greatest prime factor here that does not divide this thing. And the 2 and the 5 do divide into 80, so we're going to throw those out and we're going to have our answer be 73. Okay, great. Let's go on to the next one. So this one is a probability problem, and it says 3 fair nickels and 2 fair dimes are tossed. What is the probability that at least 2 heads are showing and that at least one of the heads appears on a dime? Express your answer as a common fraction. What I like to do in cases like this is to think about the number of heads that I have on the nickels and the number of heads that I have on the dimes, and think about whether those depend on each other. And in this case, they don't depend on each other at all. The number of heads that I get on nickels is going to have no impact on the likelihood of getting a certain number of dimes to be heads and vice versa. So since they're independent, I like to think of them as kind of orthogonal perpendicular. So I like to draw a rectangle as representing the entire probability. And I can think about the nickel probability in this direction and the dime probability in this direction. So how many options are there for a number of nickels? I could have 0 nickels, I could have 1 nickel, I could have 2 nickels, or 3 nickels that are heads, right? So this is the number of heads, nickel heads. And then dime heads, I could have 0, or I could have 1, or I could have 2, because there's 2 dimes. So basically I've got 12 possibilities for the combinations here. I've got 3 different possibilities for the number of dimes, and I've got 3 or 4 different possibilities for the number of nickels that end up to be heads. Now the first thing I want to do is just see which part of this graph, which part of this whole area, I'm going to have each of these little rectangles represent the area, the probability, the area of that rectangle will represent the probability that you get, for example, this one would be that you get 2 dimes and 3 nickels showing heads. So what is the probability that at least 2 heads are showing and at least one of the heads appears on dime? So we need at least 2 heads to be showing. So this would be 0 heads, these would be 1 head, and then these would be 2 heads, right? And so basically what we're saying, if I can highlight where there's at least 2 heads with this purple region here, it's going to be whenever you're above this line, it's going to be all this region here. And then the other thing they said is that at least 1 head has to be on a dime. Okay, so we can't have these 2 down here. Basically, we want to count the probability of all this region here, not including those 2 down there. So we're just going to basically compute the area of, or the probability that you're in any of these 7 small rectangles. Now there's many ways to do that. You could, for example, compute the area of this top rectangle and then subtract this little one here, or you could compute this rectangle and add this one here, like it's the panhandle of Oklahoma. You know, you could take the entire rectangle and subtract out this one and this one. That's another way to do it. Or I'm sorry, this one here and then this whole bottom one, I guess, because we are subtracting these 2 as well. So any one of those is fine. I think what I'm going to do is I'm going to compute, let's see, I'm going to compute the area of this rectangle, and then I'm going to subtract this one here. So basically I'm saying, what's the probability that you have at least 1 dime that is heads? And then I'm going to subtract this one case where you have 1 dime that's heads and no nickels that are heads. That should give me what I'm looking for. So what's the probability that I get at least 1 head on the dimes? Well, the probabilities here are going to be 1/4 for 0 dimes, 1/2 for 1, and 1/4 for 2. Because this is basically, you know, this is 2 choose 0 over 4, 2 choose 1 over 4, and 2 choose 2 over 4. And similarly over here, this one's going to be 1/8, and then 3/8, and then 3/8, and then 1/8. And since they're independent, you can lay it out like this and compute these individual rectangles by just multiplying these probabilities by these probabilities, because the probabilities here don't depend on this outcome. So that means that this big rectangle here, it has a width of 1, because we're not worried at all about how many nickels we have as heads. So that's 1 times, I'm sorry, I wrote this wrong. Let me fix that. This was supposed to be 1/4. I think I said 1/4, but I wrote it as 1/2. Maybe I said it wrong as well. But anyway, this is 1/4 plus 1/2 plus 1/4. They have to add up to 1, of course. And then here we have 1/8, 3/8, 3/8, and 1/8. Those add up to 1 as well. So we have this big rectangle has a width of 1, and then we multiply that by the height, which is 1/4 plus 1/2, which is 3/4. So that is our probability that we're up in here somewhere. Now we have to subtract out this part here. So we're going to subtract 1/8 times 1/2, which is 1/16. So we have 3/4 minus 1/16, 3/4 will be, let's see, 12/16. And then we subtract 1/16, and that's going to give us 11/16, which is our final answer. We can pop up in the answer key up here, or in the answer spot. All right, great. Let's move on to the next one. So this is a geometry problem. It says in the circle shown, AB is equal to CD is equal to EF, which is equal to 3. So all three of these lines that are passing through this circle have a length of 3. And it says the points of intersection among these three chords divide each chord into 3 congruent segments. Okay, well, so if they're length 3 and they're cut into 3 equal spots, that means all these little lengths are 1, right? 1, 1, 1, 1, 1. All these things, they're all 1. Okay. And it says, what's the area of the circle? Express your answer as a common fraction in terms of pi. Okay, well, one thing to be careful about with this problem is that none of these lines are diameters. We don't have a diameter drawn here, and we don't have a radius drawn. If we wanted to have a radius, it would have to go through the middle of the circle, which is in here, in the middle of this triangle. One thing you could think about is, okay, if I were to draw these lines here, I would form equilateral triangles. Maybe, I don't know, you might think about that, and you might start to think about, oh yeah, I could draw some more equilateral triangles in here. But what you'll quickly realize is that all I really need to do is to figure out the radius of this thing in order to compute the area. And the radius is just the distance from this center point out to any one of these points on the boundary. And so, for example, let's take A. I'm going to draw that a little bigger. I'm going to take my point A here, and it's going all the way across to B on the other side of the circle. And it's split into 3 pieces here. That's 1, 1, 1. And then I've got this equilateral triangle here. And at the center of that equilateral triangle, I've got the center of the circle. And so in order to find this distance from A to the center of the circle, what I really need to do is use the Pythagorean theorem with this right triangle right here. So what is this distance here? That's going to be 3 halves, because you've got a 1 plus a half of this one. That's going to give you 3 halves. And then what is this distance here? Well, if you happen to know that the distance from the base of an equilateral triangle to the center of the triangle is 1/3 of the total height of the triangle, then you can just say that this height, which you know from your special right triangles is √3 over 2, that height needs to be divided by 3 to get this portion here. So divided by 3, that's going to be √3 over 6. Now if you didn't happen to remember that, you could make some smaller 30, 60, 90 triangles like this. And when you split it up like that, you would notice that this one up here is a hypotenuse, and this one down here is one of the shorter legs. And you know that the hypotenuse of a 30, 60, 90 triangle is twice as long as one of the shorter legs, so then you can figure out that this is 1/3 of the distance here. All right, so now we just need to use the Pythagorean theorem. We've got 3 halves squared is 9/4 plus √3 over 6 squared. That'll be 3 over 36. And then we need to take the square root to get the radius. But we're actually not interested in the radius. What we're interested in is the area. So this is the radius, but what we want is the area. The area is going to be pi times the radius squared. The radius squared, we can get rid of the square root, and that's just going to be 9/4 plus 3 over 36, which is 1/12. And yeah, we just need to compute what this is. So 9/4, if we put it in a common denominator with 12, we're going to have, let's see, 27/12, I believe. 27 plus the 1, so 28/12 pi. And we still need to simplify this. We can divide by 2. We have 14. Let's see. No, I could divide by 4, can't I? Divide by 4, that gives me 7 over 3 pi. And that is my answer. 7 over 3 pi is the area. They wanted it in terms of pi, so we just put that up here. 7/3 pi. All right, great. Let's move on to problem 24. This one says Dennis rolls 3 6-sided dice. So we have another probability problem. It says yielding values of A, B, and C. What is the expected value of this big long thing, which is the absolute value of the difference between each pair? And it says express your answer as a common fraction. So one thing that I think is useful is to, when you get a problem that's a little complicated, try to come up with a problem that is easier, but might give you some hints about how to solve the harder problem. And here, one thing would be to say, okay, let's say he just rolls 2 6-sided dice. So it just has A and B instead of A, B, and C. You just have A and B, and you're going to try to compute just the absolute value of A minus B. Okay, so we can think about that. There's just a 2D grid of possibilities. You've got 1, 2, 3, all the way up to 6 here for A. And you've got 1, 2, 3, all the way up to 6 here for B. And what is this absolute difference going to be at each of those grid points if we were to make a 6 by 6 grid here? Well, if you have 1, 1, the absolute difference is 0. And the same thing for 2, 2, that's going to be 0. And for 3, 3, we're going to have 0, and 4, 4, we're going to have 0, and 5, 5, and 6, 6, we're going to have 0 there. And then as you go further and further off this diagonal, this absolute value of the difference is going to get bigger. So 1, 2, and 2, 1 are both 1. 2, 3, and 3, 2 are both 1. And we have 1 here, and 1 here, and 1 here, and 1 here, 1 here, and 1 here, and so on, right? There's one more, 1 here, and 1 here. 1, 2, 3, 4. Oh no, there's not one more. I do too many. There should be 5 of those things. And then you'll have between 3 and 1, you'll have 2. So there should be 4 2s going up this diagonal. And then there will be 3 3s. And then there will be 4 2 4s, and then a 5. So if you have a 1 and a 6, that difference will be 5. That's the biggest difference you can have. And it's symmetric going up the other way, all the way up to 5 here. So another thing you have to understand is what it means by the expected value. That's a mathematical term, mathematical definition. And if I have a probability of different value, if I have a bunch of probabilities, each associated with a different value that I can get, the expected value is basically just going to be a weighted average of those different values based on the likelihood that I get each of those values. So in this case, the expected value is going to be the probability that the value is 0 times 0 plus the probability that the value is 1 times 1 plus the probability that the value is 2 times 2, and so on all the way up to the probability that the value is 5 times 5. Those are all the possible values that I can have, 0 up to 5. So yeah, and these probabilities will add up to 1. So it's really just a weighted average of these possible values. Will give you the expected value. You can think of it as an average value too, where it's a weighted average by these probabilities. So what does this give us? One thing you can do is, because this is all symmetric, you can kind of cut this in half. Let me show you how you would do that. You could say, okay, let's take these 3 and all these ones down here. Those will be equivalent to all these ones here, up here. So since all the numbers are the same in the bottom shape and the top shape, if I compute the probability in one, it should be the same probability in the other. So that way I can divide by 18 instead of by 36. It makes it just a little bit easier. So the probability of 0, I don't actually care about the probability of 0 because I'm going to be multiplying it by 0, and that's going to give me 0. So I'm going to have 0 there, plus probability of 1. Well, I've got 5 out of 18 times 1, so that will just be 5 out of 18. And then I'm going to add the probability of getting a 2. There's 4 out of 18, but I have to multiply that by 2, so that's 8 out of 18. And then I have to add the probability of getting a 3. That's 3 out of 18, but I have to multiply that by 3, since 3 is the value, so that's going to be 9 over 18. And then the probability of getting a 4 is 2 over 18, but I have to multiply that by 4, so that gives me, again, 8 over 18. And the probability of getting a 5 is 1 out of 18, and I multiply that by 5, that gives me 5 out of 18. We just add these all together and we'll get our expected value. So it's some number of 18ths. Let's see what we've got. Let's see, I've got, if I do the 5, the 9, and the 5, that gives me 19, and then 19 and 16. That should give me, what, 35? 30, oh no, 19. Yeah, 19 and 16 is 35. So it's 35/18. Okay, but again, this is just the answer to our easier problem where we had 2 dice and we wanted to find the expected value of the difference. But the thing is, it's actually really simple to go from the answer here to the answer to the final problem, because these differences are all independent of each other. Well, they're not independent of each other, but they all have, well, let me put it this way. A minus B is independent of the value of C. So there are 6 different values you could roll for C, but this expected value of A minus B doesn't depend on what you get for C. And so you could think of instead of a 2D grid, in this case you have a 3D grid where you have A, B, and C, right? And that forms this 3 by 3 by 3, sorry, I don't know if I said that right. You have instead of a 6 by 6 grid, you have a 6 by 6 by 6 grid. It's 3D. And when you roll the dice, say A is a red die and B is a blue die and C is a green die, you could just pick one of these 216 cells in this 3D array to represent the 3 dice that got rolled. And if you think about it, basically this exercise that we went through represents what happens if you project that onto the front face here, or project it onto the side face, or project it onto the top face. And that's what these 3 sums are. And there's no difference between those 3 sums. They'll all be the same. There's no reason that the red and the blue die would have a different expected difference than the blue and the green die, for example. So that means they all have an expected value of this, and since they're all absolute values, we can just add those expected values together. And so we got 3 times this, so I just need to multiply this by 3, and that's going to be 35/6. So I would put that in my as a final answer, 35/6. All right, great. Let's move on to number 25. This one was a lot of fun. So it says there's a beetle, and the beetle starts at the point with coordinates 8, 5. So that's this guy here is where he starts. And he travels to a point on the line y = 2. So we don't know where along the line he travels to, but at some point here along this line. And then he travels to some point on the line y = x, some point along here. And then finally he travels to the point with coordinates 5, 4. So he travels up to here. This is his ending spot. And what we want to know is what is the length of the shortest possible path that the beetle could take. And express your answer in simplest radical form. So this one at first might seem really tricky because we don't know where along this line the beetle hits. We know he's going to go in a straight line to some point here. He's going to have to go in a straight line to some point here and then a straight line to here, because if he goes in a wiggly line on any of those 3, it'll definitely be longer than if he had gone in a straight line. So we know it's going to be a straight line, but we don't know where these 2 points are. If we knew where those 2 points were, we could just find these 3 distances and add them up. So again, I'm going to try to suggest that you try to think about a little bit simpler problem. Let's just think about what would happen if we had 2 points and 1 line. So let's say these are my 2 points, and I'm going to say the beetle starts here and ends here, and he's going to go and hit this line at some point and bounce up. Now, he could pick any point he wants to, but I think it's pretty obvious just from looking at it that he's not going to want to pick a point way over here, and not going to want to pick a point, certainly not going to pick a point on this side of S, because then you're going left and then back right again. So it's going to be, the point is going to be somewhere in between these 2. And you might think, well, is it going to be closer to this one or closer to that one? And you might try different things, right? You might try different points and compute these 2 distances and see what you get. And if you fiddle around with that, eventually what you'll realize is that the best point to go to is the point where you have similar triangles here and here. These two triangles, if you can make these two triangles similar, you know, where you draw a right angle here and a right angle here. Basically what that means is that this angle here has to be equal to this angle here. And at some point that's going to happen, because this, as you go from left to right, say you start with that point here, this angle is going to be really big. It's going to be up to 90 degrees if you start here, and it's going to go down to some small value here. And in the meantime, this other angle will start off quite small, and it will go up to 90 degrees by the time you get here. So at some point, those two angles will be equal to each other. And when they're equal to each other, you'll have similar triangles here. And the reason that that is the shortest path, there's a couple different ways to see that. One is by looking at just thinking about a very small increment here and thinking about how much length has been added to this one versus how much has been subtracted off that one. And I don't think I'm going to get into that, because there's a much more intuitive and easier way which I want to share with you, which really will help you as you try to solve this problem. And that is, you could take this starting point and you could reflect it across this line that you're trying to hit. And if you reflected it across that line, you would get here to this point. And now you could reflect this line about this line as well, this line segment I should say, and it would look, maybe I didn't draw that quite symmetric, but if you reflect that line segment, it would look like this. And so this length would be the same as this length. And so what you'll see is that the total distance here from here over to here and then out to here is going to be the same as if you had started down here and gone up to here and then gone over to here. And what you'll notice is that you can obviously see that this is not the optimal path between, I'm going to call this S prime, my reflected S. That's obviously not the best path from S prime to E. The best path from S prime to E is just going to be a straight line. It's just going to go straight across like this. And so that will give you a reflected path that looks like this. I didn't draw that very straight. Let me grab my straight line tool, that might help. So it'll go down like this and then up like that. And that'll be the same distance now. You know, this distance here will be the same as this distance, and then of course this is the same segment here. So that is going to be the shortest path. And one thing that you'll notice is you have some vertical angles here and here, and so those two angles are equal to each other. And not only that, but since it's reflected, it's equal to this. And so that is another way of seeing that the angle of incidence, the angle of reflection, if you want to think about it in terms of like light bouncing off a mirror, these two angles have to be equal to each other. All right, and now we're really close to solving our actual problem. Now that we kind of understand how that all works, I'm gonna start over here and just draw. Oops, I'm erasing. Oh, that's good. I'm gonna make some room here. All right, so we have our y-axis, we have our x-axis, we have our x equal y, and we have our y equals 2, and then we have our 0.85 and our 0.54. So the key here is to reflect this point about this y equal 2 axis. And if you reflect 8,5 about y equal 2, well, let's see, since it's at a y coordinate of 5, that's 3 above 2, so we have to go 3 below 2. So that's going to be 8, negative 1. So it'll be down here at 8, negative 1. And then when you reflect a point about the y equals x, that just switches the two coordinates. So this point will be 4, 5. And now we can just do our magic. We can just say, hey, let's just connect with a straight line. Let's just connect 4, 5 to 8, negative 1. Oops, let's see. Actually, yeah, I wanted to do that in a different color. Let me see if I can do that. Oops. I wanted to use my line tool too. Okay, so there we have it. That is our straight line, and what you'll find is that if you reflect this segment about this axis, we'll get this path here. Oops. Get this path here that goes to that point. And then if we reflect this section from here down about the y equal 2 line, we'll get this section here. And so this total path length is going to be our shortest path. If you were to pick any other path, you might think, oh, maybe it's better to go from here straight to this point because I'll hit both points all at once, right? Go straight from this point. Let's see, straight from this point all the way over to here with, whoops. Fix that. So we go from this point all the way to here, and then we just go from here up to here. Well, you could reflect this about this line, and what you would see is that that is actually equivalent to this path from here to here, and then this path from here to here. And obviously this path going all the way out to this point and out to here is much longer than this straight path like this. And any other path you choose, you know, that might bounce off of, bounce off of this wall and then this wall and then this wall, is equivalent to some other path like this if you reflect it. And you can obviously see that it's longer than this straight line path. So really cool little trick there for this problem. So let's see. So what do we need to do now? We just need to find the distance between 4, 5 and 8, -1. And let's see, what is that? So in x we have 4. The difference between 8 and 4 is 4. So 4 squared is 16. And then in y we have a difference of 6. So because 5 minus a -1 is 6. So 6 squared is 36. And we add those two together, and we take the square root, and that should be our answer. What does this give us? 52, so it's the square root of 52, and 52 is the number of cards in a deck with 4 sets of 13, so that's equal to 2 times the square root of 13, and that is our answer. We'll just put that up here, 2 times the square root of 13. Alright, hope you guys enjoyed that one. Let's move on to problem 6. So this one says, oh, this one was really tricky. This one says you have positive numbers x, y, and z that satisfy these 3 equations. And it wants to know the value of x squared plus y squared plus z squared. This one really is very tricky. What you can do here is you can break this up into 2 parts that each have an x and a y and a z in them. So for example, this 165 equation is xy times x plus z times y plus z. And you can try to break this up into 2 different parts that have, like I said, they're kind of symmetric and have all 3 variables. So this x you'll want to pair up with the y plus z so that you get all 3 variables. And this y you'll want to pair up with the x plus z. So then you get x times y plus z times y times x plus z. All we did was reorder things. And let's give these each a name. So I'm going to call this A. I'm going to call this B. I shouldn't draw those lines again. So let's just say this is equal to AB. And that is equal to 165. And then if you do that with these other 2 equations, what you'll find is that this one's got this one's basically C. The Z times x plus y is what we're going to call C. So that one is equal, so this 88 is C times A. That's equal to 88. And then the other one is B times C. B times C, and that's equal to 120. And we can try to find some common factors here by factoring these out. So let's see, 165 Let's see, so 165 we can factor as 5 and 33, which is 11 and 3. Let's do the prime factorization like that. And then this one we've got 11 and 8, which I'm just going to write 8 altogether. And then this one here, we got 3, 4, 2, 5. So yeah, 2 times 3 times 4 times 5. That should give us 120, right? Yeah, 20 times 6. Yep. And so now we try to find some common factors so we can identify what A, B, and C are. There's an 11 here and here. And if I remove the 11 here, there's a 15 left, and here there's an 8 left, and this is 8 and 15 here. So A, B, and C are going to be 8, 11, and 15. So the common one here is A. A is going to be 11. B is the common one here, which is 15. And C is the common one between these two, and that is 8. All right, great. So another thing we could do is we can add A, B, and C all together. And what happens if we do that? So A is equal to X times Y plus Z, which is equal to XY plus XZ. B is equal to Y times X plus Z, which is equal to XY plus YZ. And C is equal to Z times Y plus, X plus Y, we'll do them in order, which is equal to XZ plus YZ. And you'll notice that we have 2 YZs, we have 2 XZs, and we have 2 XYs. So that means A plus B plus C is equal to 2 times XY plus YZ plus XZ. And we also know what A, B, and C are. We can just add them up. 11 plus 15 is 26. Plus 8 is 34. So this is equal to 34. And now we have xy. If we just divide by 2, we have xy plus yz plus xz is equal to 17. Oops, let me fix that. 17. So the next thing to do is to look at this. Let's see. Yeah, so the next thing we can do is we can subtract A from 17. So if we subtract this xy plus xz from 17, that means I'm going to be subtracting this part and this part. That's just going to give me yz. So that means that yz, I'm going to change color. That means that yz is equal to 17 minus A, and A is 11. And so that gives me 6 for yz. And then let's see, xz. Xz is going to be 17 minus, we have to subtract these two bits, which is b. b is 15. So that means xz is equal to 2. And then, let's see, these three add up to 17, so that means that, what's the other one, xy? xy has got to be 17 minus 8. 17 minus 8 is going to be equal to 9. Okay, so now we know what xy is, we know what yz is, and we know what xz is. If we multiply those three things together, we'll get, well, actually no, let's not multiply the three together. Let's see. Yeah, if we multiply those three together, we'll get x squared, y squared, z squared. So we can write that x squared, y squared, z squared is going to be equal to 9 times 6, which is 54, times 2, which is 108. And then we can, to get x squared, we just need to divide by y squared, z squared. Well, we know yz is 6, so we just need to divide this by 6 squared and then take the square root. So well, actually, to get x squared, Yeah, to get x squared, we just need to take 108 divided by 6 squared. So we have 108 divided by 6 squared. That'll be x squared. And the thing we want is x squared plus y squared plus z squared. So let's just add, that's x squared. Then we're going to add y squared, which is 108 divided by, let's see, y squared, I'm going to have to divide this one squared. So that's going to be 4. 2 squared is 4. And then 108 divided by, for z squared, I'm going to have to divide by this 9 squared, which is 81. Okay, so my final answer should be here, if I can compute what that all is. So let's see. 108 is divisible by 6, right? So let's see. If I divide by 3, I'll get 36 divided by another 6. Oh yeah, it's just yeah, it's just, so that's just 6, right? So that's 6 plus, then I've got 108 divided by 4. Let's see. That's 27. So 6 plus 27 plus 108. I don't think 108 is going to divide by 81. 108 divided by 81. I can at least take out a 9, or actually I can probably take out a 27, right? Because 108 is 6 cubed. So I'll have, if I take out I'll have 2 cubed, which is 8 on top, divided by, let's see, what did we say? We said we were taking out a 27, so we have 3 left, 8/3, I guess. Yeah, so we just add those together. We get 33 plus 8/3. So 33 is 99 thirds, and then we add another 8/3. We get 107 thirds. 107 thirds, if I did that right. Oh wait, no, I didn't do that right. This isn't 6 cubed. This was 6 squared times 3, so this should be 3. Yeah, so this is 3, and then did I do this right? 6 squared times 3, so this should be 4 then, right? I think. And so I have 30 is 90 thirds, and I add 4 thirds. Okay, so that's going to be 94 thirds. Okay. Yeah, that should be right. 94 thirds. 94 thirds is our final answer on that one. Hope you guys enjoyed that one. Let's move on to another difficult one. This one is another geometry problem. It says in the figure shown, circle O, so that means O is the center of this circle, that's this bigger circle, has an area of 625 pi centimeters squared. Now, 625 is 25 times 25, right? So that means the radius here is going to be 25. Let's label that 25 here. And it says CD is 16 centimeters and AB is 30 centimeters. And it wants to know the area of the shaded circle, the smaller circle, which intersects points A, B, and C. Okay, so we can compute this distance OC because we know the radius is 25 and we have 16 here, so that means that little distance is 9. Another thing we could do is we can draw this line DB. So let's do that. So we go from D out to B, and we know that distance as well. No, we don't know that distance quite yet, but we know that the angle that it forms is a right angle. The reason is because we have a diameter here, and every triangle inscribed in a circle where the hypotenuse is the diameter of the circle, I shouldn't call it a hypotenuse before I say that it's a right triangle, but where the longest side of the diameter of the circle will be a right triangle. So that means this is a right angle here. And we know that this total distance from A to D is twice the radius, which is 50. So we got 50 for the hypotenuse of this big right triangle. And so this is going to be a 3, 4, 5 triangle. We have 40 here for this distance. And the next thing we can do is to try to figure out what the distance. We can label this point here where it intersects the circle and try to find the distances here. So to do this, you need to know something called power of a point. If you have a circle and you have a line outside or even inside the circle actually, and you draw two lines that contain that point, basically the distance, if you multiply the distance from this point to the two intersections of one of the lines with the circle. So in other words, this distance d1 and this long distance all the way to here, d2. If you multiply those two together, it'll be the same for this line as it is for this line. In other words, let's do a lowercase d1 for this distance to here, and then a lowercase d2 for this distance out to here. What I'm saying is that capital D1 times D2 is equal to lowercase d1 times d2. And there are a couple special cases, like you could have the line that goes tangent to the circle, then those two distances will be the same. So like let's say that's, whatever that distance is would just be squared, and it would also still be equal to these. So I've run out of d's, let's just call that t for tangent, so that would be equal to the tangent line distance squared. And you could even have, well, okay, this is also true if the point is inside the circle. You end up with lines like this. You can have the distances to the 2 points on the circle. Those two distances here and here will multiply to give you the same as what you get if you multiply this one and this one. So that's called power of a point, and we're going to use that here to compute these distances here, because what we've got here is we've got 16. Let's make a little room here. We've got 16. I'm going to even erase up here so we have a little more room. All right. So we've got 16 times, so that's this distance, times the full distance out there, that's 50. It's got to be equal to this distance, we'll call that x, times this full distance, which is 40. So this is x times 40. And we can solve for x just by dividing by 40. That gives us 16 times 5 over 4, which is just 4 times 5, which is just 20. So x equals 20. And if x is 20, that means 40 minus x, this thing over here is also 20. So this is 20, this is 20. All right. All right, well, we're getting close here. The last thing that we have to do is, let's see, we need to make a diameter of the smaller circle. And we have a right angle here, so we know that if we draw this line from A down to this intersection point, that should be a diameter of the smaller circle, which would be great to know, because then we can divide by 2 to get the radius, and we can compute the area. So let's do that. So we have a right triangle here, and we know the two legs are 30 and 20. So the hypotenuse, let's see, if I had 2 and 3, this would be square root of 4 plus 9. This would be square root of 13 here. So it's just 10 times that big. So this should be, this diameter should be 10 root 13. That's the diameter. So that means the radius is going to be 5 times the square root of 13. And now I just need to plug that into the area of the circle. So I have pi r squared. R squared is 25 times 13. And what is 25 times 13? Let's see, 25 times 12 would be 300. So I got one more 25. So this should be 325 pi. 325 pi, and that's our answer. So there you go. 325 pi. All right, that wasn't so bad. Let's move on to the next one. this one gets a little interesting. So here we have a question that asks, how many positive integer factors does this giant thing have? And the first thing you can do, which you might feel good about, is you can cancel out the 2019 factorial. And that is in fact the first step here. We have now 2020 times 2021 times 2022 times 2023. That's the 23 factorial divided by 2019 factorial. But then we also have to add 2019 factorial divided by 2019 factorial, which is just 1. So we have the square root of all that thing, and then minus 1. And they want to know how many factors that has. We still have a ways to go. One thing you can do, just to make it so you don't have to write all these numbers so often, is you can just define like an x or an n or something. Let's just say n is equal to 2020. And so this is just the square root of n times n plus 1 times n plus 2 times n plus 3 plus 1. That whole thing square root minus 1. Alright, so the next thing you need to do is figure out how can I get this to be a perfect square. And one thing you can do is you can say, well, what if I make these, maybe I could have this product be an a plus b times a minus b, so that I can get a squared minus b squared. And actually that can work pretty well. So for example, if I set a, let's say I set a to be equal to n times n plus 3. That's equal to n squared plus 3n. That's going to be the product of this one and this one. And this other one here is, let's see. Well, let's see what this other one is here. So this one's going to be n squared plus 3n plus 3. Okay. Okay, so that's, so yeah, so this thing, let's see. Yeah, and then if I multiply, it's going to be the best way to do this. I think what I want to do is I want to say that I have this thing squared. Well, okay. Let's see, that's not right. So this is supposed to be a 2 here. Okay. So this is 2 bigger than this. So I'm gonna call this a plus b and this a minus b, but it's not this a. Yeah, I'm not gonna call this a anymore. I'm just combining 2 different parts of this. So let's say this is a minus b. So that means my a has to be this plus 1. So my a is going to be n squared plus 3n plus 1. So this product, this one and this one, is going to be, that's equal to a plus 1, or sorry, a minus 1. And then this one is equal to a plus 1. And if I multiply those two together, I get a squared minus 1. And then we're going to add 1 for this one. And basically, those are going to cancel out, and I'm going to have the square root of a squared is just going to be a. So this whole thing is just going to be replaced by a here. And then I'm going to subtract 1, which is going to get rid of this. And so the whole thing is just going to be n squared plus 3n. And now I can plug back in my n. My n was 2020. So I have 2020 squared plus 6060, which is 3n. That is my number, and it wants to know how many positive integer factors does that thing have. Okay, so, well, let's see. We could definitely divide by 20. Let's make some room here. Let's make some room. We don't need this anymore. Okay, so we want to know how many positive integer factors we have from 2020 squared plus 6060. We can divide by 20, and actually I guess we can divide by, well, let's see. Yeah, so if we divide by 20, we're going to have 101 times 2020 plus 303. Okay, so now what can we divide this by? Well, we can divide this by 101, right? So that'll give us, so we're going to divide by 101. That'll give us 1 times, well, we don't need the 1 times, that just gives us 2020 plus 3. So that's also known as 2023. And if you remember the prime factorization of 2023 from math counts last year, that is equal to 7 squared times 17, I believe. Let's see, no, or is it 17 squared? Is it 50? Yeah, it must be 17 squared times 7, right? So yeah, 17 squared times 7 gives you 2023. So what did we, so if we do the prime factorization of this whole thing, basically we've got 20 is prime factorized as 2 times 5, 2 squared times 5, and then we've got a 101, and we've got a 7 and a 17 squared. So these are all the prime factors of this big thing here. And if we want to know how many positive integer factors it has, what you do is you take the exponents of all the prime factors and you add 1 to those numbers. So that'll give us 3 for this exponent added to 1. This exponent is 1, so you add 1, you get 2. And then this one, the exponent is 1, you add 1, you get another 2. This one, the exponent is 1, so we have another 2. This one, the exponent is 2, so we have a 3. And then you multiply those all together. And this gives us 8 times 9, which is 72. So there are 72 prime factors of this number. All right, great job. Let's move on. That was a hard one. Let's move on to this one. This one was really hard. This one says, in the coordinate plane, the two curves x to the fourth plus y to the fourth equals 48. And x, y equals 2 intersect in 4 points. What is the area of the quadrilateral whose vertices are these 4 points? Express your answer in simplest radical form. So you can do this just through algebra, but I think it's useful to have a picture of what's going on here too, probably. What does this curve look like? This x to the fourth plus y to the fourth equals 48. Well, we could draw our coordinate plane here. And there's going to be a point here which is the fourth root of 48. And if I go to that coordinate, fourth root of 48 comma 0, so my x coordinate is fourth root of 48 and my y coordinate is 0, that should be a point that satisfies this equation, because I take this thing to the 4th power, I'll get 48, and I add 0 to the 4th power, I'll get 48. And also this point here at 0 comma fourth root of 48. Fourth root of 48 is also on the curve, and this point here and this point here just reflecting about the origin on both of those by making this, 0 negative fourth root of 48. That's also going to satisfy it because the negative will go away when you take it to the fourth power, and then this one here, fourth root of 48, comma 0 with a negative sign here. That is also going to be on the point. So you might think, oh, maybe it's a circle. Well, it would be a circle if it was x squared plus y squared equals some constant. Since it's x to the fourth, it actually starts to bulge out a bit. It starts to look a little more squarish. And this is probably not an accurate representation, but it's something like this. It's a rounded square kind of thing. And of course, it's not really a square or a circle, but it's somewhere in between. So that's the way this function looks. And of course, this function, xy equals 2, is just a hyperbola. You've got a positive part over here. This is just the function 2 over x. And 2 over x goes over here like this. And I probably didn't draw that right. This should probably be closer in here, and this should be closer in here. But just to be clear, yeah, that doesn't have to be accurate. So I've got 4 intersection points, right? I've got the intersection point right here. Well, let's see. The intersection point right here. I've got the intersection point right here. I've got one right here, and I've got one right here. And I can make a quadrilateral by connecting those dots. And the question is asking, what is the area of that quadrilateral? So because of the symmetry of both of these curves, actually, we know that if I know the coordinate here, x, y, x comma y, this coordinate here is going to be y comma x. And not only that, but this coordinate here is going to be, let's see, negative x comma negative y, negative x comma negative y, which is just the opposite of this one. And then this one will be the opposite of that one, so it'll be negative y comma negative x. And let's just pretend for a moment that I know what these coordinates are. I would be able to compute this distance, which is the length of the rectangle, as, you know, using the Pythagorean theorem, I've got the distance that you go horizontally is just x plus y, and the distance that you go vertically is also x plus y. So this hypotenuse here is going to be square root of 2 times x plus y. And this, well, this one will be the same. It's going to be a rectangle, actually. This quadrilateral is going to be a rectangle because we've got all the symmetry that suggests that. And then let's find this distance here. So this distance we can also compute using the Pythagorean theorem. And this rise and this run are both going to be equal to x minus y. X minus y. So this is going to be the square root of 2 times x minus y. And if we multiply those two together, we'll get the area, which is just 2 times x squared minus y squared. Okay, so now I'm going to put a box around it, even though that's not our final answer. We still need to compute what x and y are, and that's going to be a difficult task. But let's go ahead and do it. I don't think we need our plot anymore. We can get rid of that. And we can just try to use algebra to figure out what x and y are going to be. Alright, let's give it a shot here. So one thing we can do is we can solve for y in terms of x. It's just 2 over x. And plug it into this equation here. So we have x to the fourth plus y to the fourth, where y is 2 over x. So this is going to be 2 over x, quantity to the fourth power. That's going to be equal to 48. And now I can multiply both sides by x to the fourth, and I can get x to the eighth plus 16, which is 2 to the fourth. The x to the fourth cancels out, is going to be equal to 48. I'm going to subtract that. Oh no, it's going to be 48x to the fourth. So I'm going to subtract 48x to the fourth to put it on the same side of the equation so that I can get quadratic in x to the fourth. So this is an eighth power polynomial, but if you consider x to the fourth as the independent variable, then it's only a quadratic. So let me write that more explicitly. So I've got x to the fourth quantity squared minus 48 times x to the fourth plus 16 equals 0. So we can solve this for x to the fourth. We really want x squared, but we'll settle for x to the fourth for now. So let's see. So we have x to the fourth is equal to, we plug it into our quadratic equation. We got minus b is going to be 48. Plus and minus the square root of b squared is 48 squared. Minus 4ac. So 4ac is going to be 16 times 4 is 64. I divide that all by 2a. A is 1, so this is just divided by 2. Alright, so let's go up here now. X to the fourth is equal to, this is going to be 24. This first part, 48 over 2, plus and minus, plus or minus the square root. Now, I'm going to put this 2 in here, and I have to make it a 4. So this is going to be plus or minus the square root of 24 squared minus 16. And at this point, I'm just going to figure out what 24 squared is. Let's see, that should be 12 squared would be 144. So 144 times 4. It's going to be 6, carry the 1. I'm going to get a 7, carry the 1. I'm going to get 576. 576 minus 16 is 560. So this is going to be equal to 24 plus and minus square root of 560. Okay, very good. I'm going to make some more room now, because this is x to the fourth. And what we really want is x squared. And it turns out that actually this is also y to the fourth. It's the plus and minus that gives us the y to the fourth as well as the x to the fourth. So the plus is going to be the x the way we had set up that graph with x being bigger than y, and the minus is going to give us the y to the fourth. So actually x to the fourth is equal to 24 plus square root of 560, and y to the fourth is going to be equal to 24 minus the square root of 560. So what are x and y? This is kind of a tricky thing here. If we want to know x squared, we know it's the square root of this thing. And what we can say is that the square root of this thing is going to have a form like this. X squared is going to have a form like square root of some number a plus square root of some number b. And when we square that thing, we'll get x to the fourth. So x to the fourth is going to be, this thing squared is going to be a, plus this thing squared is going to be b, plus 2 times the product of these two is 2 times the square root of a, b. And that has got to be equal to this thing up here. So those have got to be equal to each other. So now we've got to figure out what a and b are. We know that a and b add together to give you 24, and they multiply together to give you 560 divided by 4. We can take a 2 out of this 560. So let's change this to 2 times this. What's 560 divided by 4? That's going to be 140. So 140. So we need something. We need two numbers, a and b, that add together to give us 24, and they multiply to give us 140. And those two numbers are 10 and 14. So that means that x squared is going to be equal to the square root of 10 plus the square root of 14. And the same thing happens when you try to solve for y squared, except that you get a subtracting instead of an adding. So, and since y to the fourth does have to be, or y squared does have to be positive, y squared is going to be equal to the square root of 14 minus the square root of 10, rather than, yeah, I should probably switch these two just so you can see the symmetry. So this is square root of 14 plus square root of 10, this is square root of 14 minus square root of 10. So that's my x squared and my y squared. I need to subtract those two and multiply by 2 to get to my area of my rectangle. So if I subtract these two, the square root of 14's cancel, and I just get 2 square root of 10. And then I multiply that by 2, and I get 4 square root of 10, which is my final answer. So that was a really tricky one. We ended up with 4 square root of 10 as the answer. All right. We're almost there. We got one more. This is the grand finale here. Problem 30. It says, what is the greatest of the three prime number factors of this number here? Now, you're obviously not going to want to try to compute that number. It's very large. So you're going to need some tricks. And one thing you can do, there are probably many ways to do this, but one thing you can do is you can look at these first two and maybe we can substitute something. So if I have let's call 103 x plus 1. X plus 1 is equal to 103. And let's say x minus 1 is equal to 101. So in other words, I'm going to make x equal to 102, which is the number right in between these two. And if I make that substitution, I have x plus 1 to the fourth plus x minus 1 to the fourth. And then I have my still plus 2 to the fourth over here. So the nice thing about this is some of these terms will cancel. If you don't know what x plus 1 to the fourth is, there's a nice way of thinking about this, I think. Like when you do x plus 1 squared, you do FOIL, which is first, outside, inside, last. But that gets more complicated when you do x plus 1 to the third. And when you get x plus 1 to the fourth, it gets even more complicated. But basically what you need to do is if you have your x plus 1 here, and your x plus 1 here, and your x plus 1 here, and your x plus 1 here, you need to take all combinations of the terms and multiply them together. So there's two possibilities here, two possibilities here, two possibilities here, two possibilities here. That's going to be 2 times 2 times 2 times 2. You're going to have 16 terms over here. You know, when you had x plus 1 squared, you only had 4 terms. It was the FOIL of FOIL. Now you're going to have 16 terms depending on which ones you choose. The way I like to think about it is I like to stack my x plus 1 like this, 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 and then for each of these terms I'm just picking top or bottom. So for example, I could pick top, top, bottom, top. That would give me one of my terms, which would be x cubed, right? And then I would have to pick all those combinations to get all the 16 terms. But the thing is, those terms are all going to be either 1, x squared, x cubed, or x to the fourth. Those are the only possibilities. It's just going to depend on how many x's you pick versus how many 1s you pick. And you can figure that out by how many ways there are to choose 1 out of 4, 2 out of 4, 3 out of 4, or 0 out of 4, 1, 2, 3, 4. So basically there's a nice, it's basically just Pascal's triangle that we're using here to compute the terms. And so what you do in the end is you say it's 4 choose 4, so let me just write it out. 4 choose 4 times x to the fourth plus 4 choose 3 times x cubed plus 4 choose 2 times x squared plus, and it's x to the fourth times 1 to the 0, and then this is x to the third times 1 to the 1, x squared times 1 to the 1 squared, and then we've got 4 choose 1 times x times 1 to the third, and then plus 4 choose 0 times x to the 0, which is 1, times 1 to the fourth, which is also 1. So, you know, if you pull out your row of Pascal's triangle, 4 choose 4 is just 1, so we have x to the fourth plus 4x to the third plus 6x squared plus 4x plus 1. That's going to be x plus 1 to the fourth right here. And then x minus 1 to the fourth is going to be almost the same, except instead of doing 1 to the 0, 1 to the 1, 1 to the 2, 1 to the 3, and 1 to the 4, it's going to be minus 1 to the 4, to the 0, to the 1. And so whenever you have an even power of minus 1, it's just going to be the same as the even power of 1. But what's going to happen is now you're going to get half of these terms, or every other term, is going to be negative. So you're going to have x to the fourth is positive. You're going to have a negative 4x cubed. And then you're going to have, again, the positive on the 6x squared, and then a negative 4x, and then a positive 1. And so these, when you add them, are going to cancel out. And let me make a little room up here. What am I going to get? So that, again, that's just the, I probably shouldn't have erased all that, but that's just these two parts, the first two parts. I don't have the 16 on there yet. So if I write that out, it's 2 times x to the 4th plus 6x squared plus 1. And then I have to add this 2 to the 4th, which is just 16. And I can divide this all by, well, maybe another way to say that, I'm just going to put this 16 inside the 2. Let's see if I can just make a real quick adjustment, like we'll get this parentheses, we'll put it out there. I'm going to change this 16 to an 8. A little bit of magic there. Okay, so let's do it like that. And now what we have inside is x to the 4th plus 6x squared plus 9, right? This is just 9. And you can factor that as x squared plus 3 quantity squared times, we still have our 2 out here. So this whole thing is equal to this when x is equal to 102. So let's plug our 102 back in. This is equal to 2 times 102 squared plus 3 quantity squared. What's 102 squared? Okay, 102 times 102 is just going to be, we got a 402, 2. That's just going to be 10404. That's 102 squared. And then when we add 3, to this thing, we're going to get 10407. So we have 2 times 10407 squared. That's what this whole thing is. And now we just need to find the greatest of the 3 prime factors of this. Okay, so one of the prime factors is going to be 2. And it says there's only 3 prime factors, which means that this 10407 has got to have its prime factorization have only 2 primes. So if we can figure out what those 2 primes are, we can just put the bigger one here. So what is this divisible by? If we add the digits, we got 5 plus 7. Oh, it's 12, so it's divisible by 3. Okay, so let's put 3 into 10407. This is going to be, just do some long division here, 14. We're going to have a 4 here, 12, subtract is going to be a 20. We're going to have a 6 here. We're going to have a 2, 7, 27 is going to be a 9 there. So 3469 is one of the prime factors, and the other is 3. So our 3 prime factors are 2, 3, and 3469. And of course there are 2 of each of these ones, but that doesn't matter. We just want to know what the biggest prime factor is. The biggest prime factor is 3469. Alright, I hope you guys enjoyed that video. I'm going to do another video going through the target round and probably another one going through the team round if I can figure out those problems. So I'll see you guys then. Alright, thanks. Bye.